Hello everyone, my name is Zelko.
And I'm Ole Kröger, and we're the creators of Javis. Yeah, sure. I want to explain what Javis is to you. So Javis is an animation engine, and you can just use it to animate whatever you want with objects and actions.
Alright, so maybe let's start with the basics. So, for example, you can create a square, a circle, text, or anything that you might want to draw. Right, so using these objects, we can actually animate them. So for example, we can translate and rotate them, morph them, or even make them disappear.
Well, what if I tell you that actually one of us three is created with Javis?
And well, I don't think that's going to be me.
I don't think it's me either. That's right, you are created with Javis. And we have full control over you.
We can even do this.
Okay, Jacob, let's stop there.
Absolutely! We can go through some of the technical details of what makes Javis a powerful animation engine and get you started with making your own animations. So, are you ready to dive right in? Alright, well, let's go. Now, to get into more of the technical details about what makes Javis Javis, we must first ask ourselves the question of what makes an animation engine? Animation engines have three distinct qualities where they can create objects, render objects, and animate objects. What we mean by objects is that they can be as simple as squares or circles, or a user-defined object that the animation engine can render, animate, and finally output and make per how the user wants to see it using the tools provided by an animation engine. Moving forward, three common animation engines are the Manim Community Edition, Javis.jl, and Processing. Seen here are three GIFs which are highly similar, and in the following slides we'll cover the code used to create these three similar GIFs as they relate to the animation engines. Keep in mind, Manim is written in Python, Javis in Julia, and Processing in Java. As I said before, Manim utilizes Python and really leans into the object-oriented paradigm provided by Python. As you can see in lines 5 and 6, we use the class-based approach, and seen in line 8 through 10, as well as line 3, we also see utilization of the namespace happening with Python. Now, Manim provides a lot of convenience methods for creating basic polygons, such as circles or squares, as well as easy-to-apply transformations where we can render an animation how we might want to see it. Furthermore, Manim provides an easy-to-use command line tool where you can define the output format of an animation that you're creating, its quality, as well as, by using Python scripts, the full animation or specific scenes from that animation. Moving on to processing, I'll discuss some of the differences between processing and Manim in the next slide.
Thanks, Jacob. Yeah, as mentioned before, processing is written in Java, and it has a completely different paradigm. We have a setup function and we have a draw loop. So the basic drawing functions are provided in processing, like circle, rectangle, and other shapes, but not much more. And the draw loop is a frame-by-frame loop which renders to the animation, which makes it very flexible but the interaction between objects has to be computed manually. So in this case, we increase the angle in each frame to have the view of an animated or rotated circle in the end. So let's talk a little bit more about Javis. It provides a balance between flexibility and convenience functions. So we have the flexibility to provide frames for each object and the convenience functions of things like a circle in line 7. And we can also use user-defined functions for objects, like from line 5 to line 8, which is used in line 12, where we have a colored circle. And the animation itself is done by acting on objects, as you can see in line 13, where we provide an action which is used to rotate the red ball around the center of the origin. As you have seen, we have 3 different types of paradigms in these 3 different animations engines: Manim, Javis, and processing. So let's focus a little bit more on Javis. First of all, let's talk a little bit more about frames. Frames are very fundamental to Javis animations. Each object, like the red ball and the blue ball here, need to define frame ranges, which define when they are visible, and the actions define frame ranges as well to see when they act on the objects. And below you see 3 different frames of the animation on the right. And now more to actions. So the actions here are different for the red ball and the blue ball. The red ball just rotates around the center, which gives the animation life, but is quite boring. The blue ball instead rotates around the position of the red ball, so they interact with each other. And now to the qualities of Javis. So as you have seen before, Javis has a different paradigm than the other 2 frameworks with this object and action relationship. And as it is written in Julia, it integrates very well into the Julia ecosystem. So on the right-hand side, you can see a graph animation, and we want to also provide more animations for linear algebra, physics, and more. And now Jacob will tell you more about workflows for Javis, ranging from notebooks to streaming.
All right, thank you, Ola. So before we dive into notebooks, I want to take a moment to actually step-by-step go through an actual Javis script to create an animation in Javis. The animation that we're creating, you've actually already seen before, or at least a version of it when you first joined our presentation. So stepping through the code, we obviously need to install or use the Javis package. Furthermore, for this particular animation, we're going to use the animations and colors.jl packages, which both provide easing functions and colors for us to use. More on easing functions in a bit. Our first function here is the ground function, which simply defines the background of our animation, in this case, black. Moving forward, we approach our next object, which is rather different, and is called animation. It comes from animations.jl. Now, what we use animation objects for in Javis is to define how objects can move and at what rates they move. If you notice, when the balls start from the center of the circle and move to the outside perimeter, they actually move at varying speeds, going fast at the start and slowing down towards the end. That is called an easing function that we use with Javis. For this one, we're using the sign.io easing function. Similarly, we define sign.io easing functions for the balls moving out from the origin of this frame, back into the origin of the frame, and also the balls moving around the outside perimeter of their path. And finally, we get to another specific type of animation that we use here, which, if you can guess by the name of it, color anim, defines how the colors change for the balls. In this case, we change the colors from red, cyan, and finally to black. And we use, the sign.io easing function. Moving forward, we use the video object to define where we want to draw all these objects onto, and also the frame size of the animation. and we define our background for the rest of the animation going forward. Now where we get into the really exciting part is with this loop that you see below. This loop creates 5 balls that you see in the animation, starting at different points in the animation. Furthermore, it uses animations to define the rate at which various actions occur, such as rotations. In this case, not only are rotations used, but appearing and disappearing are used, scaling is used, and rotation around various points are used. As you can see, the balls rotating around the origin of the frame. Finally, we get to kind of the most exciting part, which is rendering our animation. And once we render this animation, we end up with this beautiful animation that you can see on the right. Now going forward, I'm going to show you how this animation can be made on different workflows involving Jupyter and Pluto notebooks, as well as with streaming. So let's dive in, starting with Jupyter notebooks. So here we are in a Jupyter notebook. Now I'm going to assume that most of you are actually already familiar with how Jupyter notebooks work, so I'm not going to go into detail about that. Rather, what I want to draw your attention to is how I've taken the code in the previous example and broken it up across the cells that you see here in this Jupyter notebook. This is a great way to organize your code when you're creating a Javis animation, to keep track of your animations, videos, actions, and objects as you create an animation. Now finally, we get to a very exciting aspect of the Jupyter workflow for creating Javis animations, and that is with the render function. Here, if we set the keyword argument Liveview equal to true and run this cell, we actually get a widget that appears below that cell. This widget is a slider, and if we move it up and down, we can actually see each individual frame of our animation being generated in real time. We can even query specific frames. This is a great tool for if we want to do sanity checks or to see how an animation is being created as you're working. Now, unlike other notebooks, Jupyter notebooks do have one drawback, and that is they lack the reactivity that you can see in other notebooks. For example, I just changed that animation from red to green, so we should see red balls, we should see green balls instead of the red balls. But rather, we still see the red balls appearing. Now for that reactivity, we'll need to transition to another notebook, Pluto notebooks. So let's go over there. So here we are in a Pluto notebook finally. As you can see, the cells look rather similar to Jupyter notebook. And if you notice, we actually use one additional package that we weren't using in Jupyter, and that's called Pluto UI. I'll explain what that does a little bit later in this presentation. Furthermore, Pluto comes in with built-in inspection tools that we can actually use to help with the creation of Javis animations. For example, if I highlight the animation object here, I can pull up quickly the docstring associated with animation. This can be very useful for when you're wanting to create animations on the fly. Moving forward, if you notice, with our for loop that creates the balls that belong to our animation, to utilize the reactivity found in Pluto, we actually have to set the for loop inside of a begin and end statement. Moving forward, you'll see that once we render the GIF, we actually end up with a frame carousel of images showing each individual frame of the animation. This is useful for just a quick inspection check and a quick sanity check to make sure your animation is being made properly, and also to compare it to the previous frames to see if it's going in the right way that you expect it to. Finally, again, by setting the live view to true and using the Pluto UI package, we are able to actually create another slider object similar to what you saw in Jupyter Notebook. So moving on to the really exciting aspect of Pluto, which is the reactivity. If we take the color anim function that we talked about earlier that defines colors being used in animations, we can actually see by changing the color of red here to green, we'll see not only does the green here change, but if we look at the frames that we were looking at before, those are no longer red, the balls are now green. Furthermore, if we go to the slider, we see that green balls appear at the beginning rather than red balls. So, as you can see, notebooks provide a very exciting and useful workflow process for creating animations using Javis. We're very excited to see how individuals in the future will be using notebooks to both create animations and share them with others. Now, before we move away from talking about workflows involving Javis, there's actually 2 additional things that I want to talk to you about. The first is the Javis viewer. If you don't want to work in a Pluto or Jupyter Notebook environment, have no fear. Javis actually comes with a built-in image viewer or animation viewer directly inside of its own package. For example, if we remove the path name keyword argument from the rendering process and substitute Liveview equals true in this process, and rerun our script and using Javis to create this animation, you'll see in our icon bar a new window pop up called the Javis viewer. And inside this window, once we click on the app icon, we can use our keyboard to arrow through the different frames of an animation. We can click the buttons on the right hand and left hand sides. We can move the slider around to view our animation frames on the fly. And similar as you saw before, we can even jump to a specific frame if we so choose. This is useful for if you don't want to work in a Jupyter or Pluto environment, you don't have access to one, or if you just want to quickly set up something in your scripting process to see how your animation is being created. Number 2 that I want to show you is in lines 96 to 97. If we comment out line 94 and instead uncomment lines 96 to 97, we can actually set up Javis to stream an animation that is created over a UDP process. So for that, we're now going to save the file, provide the keyword argument streamword config equals stream conf, and once we do that, we're going to include the code, and in our notebook, well, not our notebook, but rather in our REPL, we'll see that we have this information pop up. No streaming, we're not streaming anything currently, and now a live stream has been started. Now to show you how this works, I'm going to open up the VLC media player. Once this is open, I'm going to go to media and click open network stream. Here, I'll type in the port that you saw pop up from VS Code. Once we do that, we can click play, give it a moment, and you can actually see our live animation being broadcasted over UDP network in real time. This is very useful for if you want to quickly share an animation that you've created over a local area network to your colleagues, your friends, or anyone who might be interested in seeing your animations. So again, Javis provides a variety of different workflows that you can use to illustrate and show what you're creating and envisioning very quickly and rapidly. We're excited to see how these workflows continue to evolve and adding new platforms as they become available to Javis.
All right, let's have a look at some educational purposes of Javis as well as other animations that are done by the community. First of all, I created a video about how to solve Sudokus using a computer program a couple of weeks ago, and all the animations are done with Javis. Some of the animation you can see here. Furthermore, I used it on several of my blog posts. In one of them, I created a Fourier transform, and I used all these animations that you can see here on that blog post. And Javis is also used by the community already. On the left-hand side, you can see an animation that is used in a blog post as well for mathematical educational purposes. And on the right-hand side, you can see a more artistic animation, which is done by one of our community members.
And to also explain to you all the flexibility of Javis, to give a small case study in an application area for the domain of neuroinformatics, I actually use Javis for all the animations that you see here. I use it to create a 1020 EEG electrode array, which is the metal bits that you put on the skull to record brain activity. So I created a channel, and then using Javis, I actually was able to create an EEG topo map, which you see in the center. And finally, I was able to create an EEG topo plot with the electrodes overlaid on top of the brain activity. So as you can see, Javis is extremely flexible and has wide application across not only many different use cases, but also for very specific and niche domains.
And now let's have a look at the immediate next steps for Javis. Currently, there are 2 Google Summer of Code students that are working for us, Ash Sharma and Debrabata Mandal, and they are working on layers, so that's possible to combine several objects in one layer. We want to improve object positioning, so general ease of use of Javis can be improved. We want to go more into graph animation and improve morphing. And later on, we want to also support live streaming to multiple platforms for informative content. And after that, we want to organize Javis a little bit more by splitting it up into at least three different categories, by also creating a Javis organization on GitHub. And we plan to split it up to Javis Math, Javis Graphs, and Javis Physics, and maybe more in the future. And now it's your time to get involved with Javis. First of all, you can see docs, tutorials, and of course our codes on GitHub. And we are looking forward to your issues, pull requests, and general ideas. And if you just want to have a chat with us and have your ideas bring into Javis, you can also check out our Zulip channel. And we want to thank Grant Sanderson, Daniel Schiffman, and Chameleon for their inspiration of us to create Javis, as Grant Sanderson is working on Manim, Daniel Schiffman is working a lot with processing, and Chameleon is the creator of Luxor, which is the backend of Javis. And we also want to thank our Google Summer of Code students again, Ash Sharma and Debarata Mandal, which you've seen before, and they continue their work on Javis in the upcoming months. We also want to thank everyone else who contributed to Javis already, which are all those people you can see here on the right. And they worked on documentation, bug fixes, and just providing interesting examples for our example section in the documentation.
So we hope you enjoyed our presentation, and we look forward to seeing the animations that you come up with in the future using Javis. Thank you, everyone.
Bye.